Hello, welcome to EPG Pathshala Biophysics, Paper 2, Quantum Biophysics. I am Angshuman Lahiri, Associate Professor, Department of Biophysics, Molecular Biology and Bioinformatics, University of Calcutta. In this paper, today we are going to take up Module 13, that is Huckel Molecular Orbital Theory. We have already discussed in the previous modules the valence bond method and hybridization and other concepts. It is definitely possible to apply the valence bond method to understand the electronic properties of benzene and other aromatic hydrocarbons, but the calculations become somewhat complicated. Instead, in this module, we shall discuss a simple treatment of conjugated and aromatic molecules, which was forwarded by Hückel in the 1930s. This method, along with its various extensions and modifications, has been applied widely in organic chemistry and has come to be known as the Huckel Molecular Orbital Theory. As we have already discussed briefly in the previous module, the principal assumption in the Huckel molecular orbital theory is that the pi electrons move in a fixed effective electrostatic potential due to the sigma core of the molecule. And the sigma electrons are thought of as localized, and the pi electrons are described by molecular wave functions that extend over each of the atoms that contributes a pi electron. This gave rise to a very important concept of delocalization of pi electrons. In this module, our objectives are to learn in more detail about the Huckel molecular orbital method, to review and explore examples of its applications, to examine some general results concerning the Huckel molecular orbital method. In the previous module, that is module 12, we discussed a simple way of treating conjugated carbon compounds quantum chemically, considering their pi electrons explicitly. In organic chemistry, a conjugated system means a molecule or a molecular entity which may be represented as an alternating system of single and multiple bonds. For example, one such example is CH2 double bond CH, single bond CH, double bond CH2. However, conjugated systems can have other atoms than carbon, such as CH2 double bond CH, single bond C, triple bond N. The important point is that each contiguous atom in the chain should have a p orbital, and conjugation leads to the interaction of one p orbital with another over an intervening sigma bond. The interacting p orbitals give rise to the pi bonding in the conjugated system. One important property of such pi bonding in conjugated systems is that the bond is not strictly localized between two atoms. Thus, such systems are characterized by partial or fractional double bonds, and we can talk about a delocalization energy corresponding to the stabilization of the system compared with a hypothetical system with localized single and double bonds. So let us now go to Huckel molecular orbital theory, and first let us know a little bit about Erich Hückel, who actually proposed this method. Erich Hückel was a German physicist and physical chemist. In his early years, he worked with, among other famous scientists, Max Born, one of whose contributions, the Born-Oppenheimer approximation, we have already discussed in Module 9. With Max Born, Hückel worked on the quantum theory of polyatomic molecules, and this exercise trained him in quantum mechanics and also aroused his interest in matters related to molecules. In modern day parlance, we may call the subject area of his research as chemical physics. Afterwards, he worked for some time with Peter Debye, a Nobel laureate in chemistry, which led to the formulation of the famous Debye-Huckel theory of electrolytic solutions. In the 1930s, Hückel gradually became more interested in the new developments that were taking place in the area of quantum mechanics and were being carried out by his compatriots such as Pauli, Heisenberg, and others. His first major work in this area was to construct, on the basis of quantum mechanics, a theory of double bonds in molecules such as ethylene. Through his quantum mechanical model, he tried to explain the characteristic stabilizing distribution of electrons in a double bond. After being successful in formulating a convincing model of the double bond, Hückel finally turned his attention to conjugated and aromatic molecules such as benzene. In the following few slides, we will cover a few aspects of the theoretical model, which is now called the Huckel Molecular Orbital theory. Let us briefly recapitulate the mathematical steps that we used in the previous module. We suppose that for our system we can treat separately the pi electrons from the sigma electrons. Next, we set up a basis of the pz orbitals, one for each atom donating a pi electron. We now seek molecular orbitals that are linear combinations of these pi electronic atomic orbitals that minimize the energy of the system. We have already seen how to construct such a molecular orbital. The molecular orbital, for example, capital Psi, has to be written as C1 Psi 1 plus C2 Psi 2 plus up to Cn Psi n, where we have capital N number of atomic orbitals Psi n. The coefficients Cr need to be determined from a minimization condition. Let us now consider the energy of this molecular orbital. The energy epsilon is given by this equation, where in the numerator we have the matrix element of the Hamiltonian, and in the denominator we have the overlap integral of the molecular orbital. We seek the coefficients such that the energy is optimized in the sense that the first derivative with respect to the coefficients all vanish. That is, we require that del epsilon del Cr is equal to 0. A simple calculation shows that this leads to the matrix equation sum over R H SR minus epsilon S SR into Cr equals 0, where H SR is the Hamiltonian matrix element and S SR are the overlap matrix elements. In the Huckel approximation, the overlap matrix elements S SR or RS equals 1 only if R equals S. Otherwise, it is taken as 0. For an all-carbon system, we take all the diagonal elements of the Hamiltonian matrix to be equal to a parameter alpha, that is, HII equals alpha. The off-diagonal elements between the nearest neighbor orbitals are set to a parameter beta, and all others are set to 0. Since the matrix equation that we constructed will have non-trivial solution if the determinant is 0, that is determinant of H minus epsilon S equals 0, this will give us a polynomial equation in epsilon of degree n, where n is the number of atomic orbitals used to construct a molecular orbital. Since such polynomials will have exactly n solutions, there will be n molecular orbitals or sets of coefficients Cri with energies epsilon I. So there will be as many sets of solutions Cr as there are functions in the basis. Let us therefore label the coefficients as CRI, where the index I refers to the molecular orbital and R refers to a site. Next, we will examine some general results for some special types of systems. It has been possible to solve the Hückel equations in a general manner for a few special situations. These include, for example, cyclic polyenes of arbitrary sizes and also linear chains of arbitrary length. Let us first take up the case of cyclic polyenes. Let us consider a cyclic polyene which is a ring of n sites. In such a ring, site R will be connected to sites R plus 1 and R minus 1. It also has to satisfy the boundary condition due to ring closure, that is CRN equals Cn plus R, where small n is the label for the molecular orbital and capital N is the number of sites. One can easily verify that for such a system, a rho in the Hückel equation will be given as in this equation alpha minus epsilon n into CRN plus beta into CR plus 1n plus CR minus 1n equals 0. To solve these equations, let us take as guess the following solution. CRN equals e to the power I 2 pi nr by capital N. We can easily convince ourselves that this satisfies the boundary condition, because if we replace in this equation R by capital N plus R, then e to the power I 2 pi n capital N by n gives 1, so that it becomes CRN. Now let us substitute the guess solution into the Hückel equation. After factoring out the common term, we shall be left with alpha minus epsilon n plus beta into e to the power I 2 pi n by n plus e to the power minus I 2 pi n by n equals 0. From Euler's formula, we know that cos theta equals e to the power I theta plus e to the power minus I theta divided by 2. Using that relationship, we finally have epsilon n equals alpha plus 2 beta cos 2 pi n by n, where n equals 0 plus minus 1 plus minus 2 up to capital N by 2 for even n, and n equals 0 plus minus 1 plus minus 2 up to plus minus capital N minus 1 by 2 for odd n. There are precisely capital N molecular orbitals for these capital N sites. Since cos x is an even function, this means that apart from n equals 0 and n equals capital N by 2, the energy levels for cyclic polyenes will occur in degenerate pairs. This feature of the energy levels of the cyclic polyenes has an interesting consequence that is reflected in the Hückel 4n plus 2 rule that we shall discuss later. Next, we go over to linear polyene chains. We can use a similar trick for a linear chain of n identical sites. In this case, we shall choose as the boundary condition that the wave function becomes 0 at both ends. So, if we label all the atomic sites as 1, 2, capital N, the relation that must be satisfied is C0n equals C capital N plus 1 n equals 0, where the small n as before labels the molecular orbital. Let us take as guess solution a sign function such as CRN equals sin n pi r by n plus 1. Putting r equals 0 and r equals n plus 1, we can see that this function becomes 0 satisfying our stipulated boundary conditions. Now, as before, we substitute it in the Huckel equation and we get a somewhat long expression governed by this equation: alpha minus epsilon n sine n pi r divided by n plus 1 plus beta sine n pi r plus 1 divided by n plus 1 sine n pi r minus 1 divided by n plus 1 equals 0. To simplify this, we use the identity sine a plus minus b equals sine a cos b plus minus cos a sine b. So the equation becomes alpha minus epsilon n sine n pi r by n plus 1 plus beta sine n pi r by n plus 1 into cosine n pi by n plus 1 beta sine n pi r by n plus 1 into cosine n pi by n plus 1, that is equal to 0. So finally we get, after removing all the sine terms, epsilon n equals alpha plus 2 beta cosine n pi by n plus 1. This looks similar to the energy level expression obtained for the cyclic polyenes, but actually they are not identical. An important difference is that the linear chain lacks the doubly degenerate energy levels that were present in the cyclic system. So let us take some particular examples like butadiene. Butadiene, that is C4H6, is a planar chain molecule having 4 pi electrons in a row. We can think of the formation of butadiene as 2 ethylene molecules joined by a covalent bond. Now we can use results from our previous derivation of energies for a linear polyene chain. And since n equals 4 for butadiene, we have the energy levels as epsilon n equals alpha plus 2 beta cosine n pi by 5. Putting n equals 1, 2, 3 and 4, we get up to the first decimal places. Epsilon 1 equals alpha plus 1.6 beta, epsilon 2 equals alpha plus 0.6 beta, epsilon 3 equals alpha minus 0.6 beta, epsilon 4 equals alpha minus 1.6 beta. Since the Huckel parameters alpha and beta are both negative, epsilon 1 has the lowest energy. Both epsilon 1 and epsilon 2 having energy levels below alpha correspond to the bonding orbitals pi 1 and pi 2. All 4 pi electrons in the ground state of the molecule fill up the 2 bonding orbitals. The remaining 2 energy levels correspond to the antibonding pi 3 and pi 4 orbitals. So in this figure you can see how the energy levels are for butadiene and how the 4 electrons are filling up the 2 bonding orbitals pi 1 and pi 2. Now by definition, epsilon 2 is the energy of the highest occupied molecular orbital or the HMO. Similarly, epsilon 3 is the energy of the lowest unoccupied molecular orbital or the LUMO. The most preferred transition in a molecule is from HMO to LUMO, and the energy cost corresponding to it is taking beta equals minus 2.8 electron volt, delta epsilon equals epsilon 3 minus epsilon 2, and that is equal to minus 1.2 beta, and that should be equal to 3.4 electron volt. This being the minimum energy, this transition takes place at the longest wavelength called the characteristic absorption wavelength of the molecule. From the energy level occupation at the ground state, the total ground state energy of butadiene comes out as epsilon 0 equals 2 epsilon 1 plus 2 epsilon 2, and that is equal to 2 into alpha plus 1.6 beta plus 2 into alpha plus 0.6 beta, that is equal to 4 alpha plus 4.4 beta. Here we have very conveniently ignored the repulsion among the electrons. If we consider that the total energy of the 2 pz electrons in the 4 isolated carbon atoms is 4 alpha, the lowering of energy due to the formation of the pi bonds is 4.4 beta. The magnitude of this energy is the total delocalization energy for the pi electrons in butadiene. The pi energy per electron is then the absolute value of 1.1 beta, which is about 3.1 electron volt. If we compare this stabilizing energy with that in ethylene, which was found to be the absolute value of 2 beta in the previous module, we observe that the butadiene molecule has an extra stabilization of absolute value of 4.4 beta minus 2 into mod 2 beta, that is equal to mod 0.4 beta, that is roughly equal to 1.1 electron volt. Such stabilization may have favored the polymerization of molecular units rich in pi electrons during prebiotic evolution. In the previous module, we have seen how to write the Huckel matrix equation in terms of the variable x, where x was equal to alpha minus epsilon by beta, and indicated how to obtain the expansion coefficients CR in the molecular orbitals. If we carry out that exercise for butadiene with the values of epsilons substituted and take care about the normalization, we get the following values for the lowest orbital: C1 equals 0.37, C2 equals 0.60, C3 equals 0.60, and C4 equals 0.37. In the same manner, we can calculate the coefficients for the other 3 orbitals. So, these 4 orbitals can be written as capital Psi1 equals 0.37 Psi1 plus 0.60 Psi2 plus 0.60 Psi3 plus 0.37 Psi4 for the first molecular orbital. For the second molecular orbital, Psi2 is equal to 0.60 Psi1 plus 0.37 Psi2 minus 0.37 Psi3 minus 0.60 Psi4. And similarly, we can see the expressions for the molecular orbitals Psi3 and Psi4 in terms of the atomic orbitals Psi1, Psi2, Psi3, Psi4. We have thus obtained all the energy levels and molecular orbitals of the pi electrons in butadiene, and this solves our problem for this molecule. Let us now take the case of a planar ring molecule such as benzene. It has 6 delocalized pi electrons, as you can see in the figure, so that in our formula for cyclic polyenes, we shall put capital N equals 6. Let us remember that formula once again. It was epsilon n equals alpha plus 2 beta cos 2 pi n by capital N. For capital N even, n runs from 0 plus minus 1 plus minus 2 to capital N by 2. Putting the value of n equals 6, we get the successive energy levels. Epsilon 1 equals alpha plus 2 beta, epsilon 2 and 3 are degenerate energy levels and they are equal to alpha plus beta. Epsilon 4 and 5 are again degenerate and have a value alpha minus beta. Epsilon 6 is equal to alpha minus 2 beta. So, in the figure you can see all these energy levels of benzene, and all the 6 pi electrons are accommodated in the lowest 3 bonding orbitals with energies alpha plus 2 beta and alpha plus beta. So the lowest energy level alpha plus 2 beta are occupied by 2 electrons, and the degenerate levels alpha plus beta are occupied by 4 electrons. Thus all the bonding orbitals in benzene are completely filled. Again, we completely ignore the repulsive interaction between the electrons and calculate the total energy in the ground state. The ground state energy, that is epsilon 0, is 2 epsilon 1 plus 2 epsilon 2 plus 2 epsilon 3, and that comes out as 6 alpha plus 8 beta. Therefore, the net pi energy for benzene is mod 8 beta, and the pi energy per electron is mod 1.33 beta, which is about 3.7 electron volt. The estimated energy for the HOMO to LUMO transition is delta epsilon, that is equal to alpha minus beta minus alpha plus beta, and that is equal to minus 2 beta, which is equal to 5.6 electron volt. We now obtain the molecular orbitals Ψ1, Ψ2, Ψ3, Ψ4, Ψ5 and Ψ6 by solving the Huckel matrix equation as before and taking into consideration the normalization constraint C1 square plus C2 square plus C3 square plus C4 square up to C6 square equals 1. The final equations for the molecular orbitals look like this. Ψ1, the first molecular orbital, equals 1 by root 6 Ψ1 plus Ψ2 plus Ψ3 plus Ψ4 plus Ψ5 plus Ψ6. Ψ2 equals half Ψ1 plus Ψ2 minus Ψ4 minus Ψ5, and the rest of the molecular orbitals are as follows. So this is the occupancy of the energy levels in benzene. So this also solves the Huckel equation for benzene by finding the energy levels and the molecular orbitals for the pi electrons. Interestingly, although the lowest energy level in benzene is not degenerate in energy, the other two bonding orbitals are doubly degenerate. Again, the highest energy level is not degenerate, but the other two antibonding orbitals are doubly degenerate. We shall find that this obeys Hückel's 4n plus 2 rule for aromatic hydrocarbons. So what is Hückel's 4n plus 2 rule? According to Hückel's 4n plus 2 rule, cyclic conjugated planar molecules are aromatic if they contain 4n plus 2 pi electrons and anti-aromatic if they contain 4n pi electrons. The term aromatic is usually used to describe a cyclic planar molecule that exhibits significantly increased amount of stability. In the bonding orbitals of benzene, for example, we find that the distribution of 6 pi electrons to be consistent with the 4n plus 2 rule if we take n equals 1. This value of n actually implies that benzene has only one doubly degenerate energy level with 4n equals 4 pi electrons above the lowest non-degenerate energy level filled with 2 electrons. Considering naphthalene, which has a double ring, we find that the number of pi electrons is 10, so that n equals 2. For this case, the rule predicts two doubly degenerate energy levels consisting of 4n equals 8 electrons above the lowest energy level filled with the remaining 2 electrons. Similarly, anthracene, a triple ring aromatic compound, has 14 pi electrons corresponding to n equals 3. As before, this means that in anthracene, the pi electrons are distributed in 3 doubly degenerate energy levels consisting of 4n equals 12 electrons above the lowest state filled with the remaining 2 pi electrons. A related concept is anti-aromaticity. Anti-aromatic compounds have cyclic pi electron systems with 4n pi electrons. In contrast to the aromatic compounds, they are characterized by high instability and reactivity. It appears that Hückel's 4n plus 2 rule can only be justified for monocyclic systems like benzene, 10-aniline and 14-aniline. So the results for naphthalene and anthracene showing degenerate energy levels according to the 4n plus 2 rule may be considered empirical and approximate. In a certain sense, the highly stable aromatic hydrocarbons have a pi electron distribution like closed shell atoms like helium or neon. In the case of the aromatic molecules, the closed shells consist of bonding orbitals with all the energy levels fully occupied by pi electrons according to the Hückel's 4n plus 2 rule, where n equals 1, 2, 3 and so on. Let us now briefly discuss some interesting results for alternate and non-alternate hydrocarbons. Alternate and non-alternate hydrocarbons differ in the way their carbon atoms can be classified. In an alternate hydrocarbon, the carbon atoms can be divided into two sets in such a manner that no element of either of the two sets has an element from the same set as a nearest neighbor. Coulson and Rushbrook observed in 1940 that a large number of conjugated hydrocarbons are alternate and have a number of similar properties. It is easy to convince oneself that a hydrocarbon will be alternate if it does not possess an odd-membered ring. Consequently, all linear chain hydrocarbons, as well as molecules consisting of fused benzoid rings, such as naphthalene, anthracene, etc., are alternate. Molecules like azulene with odd-membered rings are non-alternates. In the figure, you can see one example of an alternate hydrocarbon and a non-alternate hydrocarbons, where we have separated the two classes of carbon atoms by starring and non-starring. So the starred carbons belong to one class of carbons and the non-starred carbons belong to the other set of carbons. And we separate these alternate and non-alternate molecules by looking at whether the starred carbons have as nearest neighbor only non-starred carbons and non-starred carbons have as nearest neighbors only starred carbons. Now these alternate systems can be further subclassified. The system is even alternate if equal numbers of starred and unstarred carbons occur. It is odd alternate if the numbers in the two sets are not equal. Since we always maximize the number of stars, this means that odd alternate systems will have more starred than unstarred atoms. In the figure, A, like all linear systems, is an alternate hydrocarbon. The ones with even numbers of atoms are even alternate. With odd numbers, they are odd alternate. In the figure again, structure B, naphthalene, is an even alternate species having 5 starred and 5 unstarred carbons. Now, Huckel theory predicts the following properties for alternate systems. The energy levels of alternate hydrocarbons are symmetrically placed about an appropriate zero level, and that is alpha. This implies that an odd alternate hydrocarbon must possess a non-bonding orbital. The coefficients of expansion in atomic orbitals for the molecular orbitals of an alternate system are identical for any pair of complementary orbitals except for a change of sign on the unstarred atoms. Let us now briefly summarize the important points of this module. We made the assumption that the pi electron energy can be minimized independently of the sigma electrons. This separation between pi and sigma electrons is an approximation. Another assumption is that each pi electron feels the same field so that they can be treated as independent particles. Except for the use of the Pauli exclusion principle, no explicit use was made of electron spin. The Huckel method uses the LCAO-MO approximation. Next, the Huckel determinant corresponds to the connectedness of the molecular system and is independent of its geometric variations. The energy of each molecular orbital is expressed in terms of two parameters, alpha and beta. Thank you.